All right. The next talk is a long presentation by Nathan Maillet, who is a PhD student at LAAS-CNRS, the former lab I mentioned during the introduction. The presentation is titled Brace Yourselves, Key Recovery from Side Channel Power Analysis Attacks on Non-SIMD HQC Decryption. So if you didn't get it, as I didn't, initially, this is about, a breaking HQC implementation that would be production ready using side channel attacks. If you're ready, you can. The floor is yours.
Hello. All right, so let's speak about some side channels, shall we? I will present to you a joint work with Cyrius Nugier, Vincent Migliore, and Jean-Christophe Deneuville. And just to remind you of some keywords, let's speak first of side channels. So when you are doing some computation, you can view it as a black box, or you can think of it as a physical process being done by your CPU. And during the computation, if you have anything like timing or the electromagnetic field, which depends of the secret, well, if you measure it, you have some dependence of the secret, and you can retrieve some information from it. And it's the same from the power consumption and variation of the power consumption. And so I will talk about key recovery from side channel power analysis attacks on non-SIMD HQC decryption. So SIMD stands for single instruction multiple data, which is some kind of parallelism. And HQC is a key encapsulation mechanism based on asymmetric crypto. All right, so for the power consumption, well, when you measure the variation of the power consumption, you can have some models based on the general purpose registers, and it's leaking some information, and some attacks have been made which uses such information. For instance, we have Platypus, which uses the Intel Rappel monitoring, which is some kind of monitor in your CPU in order to send to the kernel some information about the power consumption of the CPU. And Platypus is an attack taking advantage of it. So it breaks the kernel ASLR. It can leak some IRS keys using Intel NI, which is some extension of the instruction set for cryptographic instructions. And it leads to two CVEs, both of them having a CVSS of 5.5. So it's quite important. And we have another one, for instance, Heartbleed, which is a power to timing side channel. It's using DVFS, so dynamic voltage and frequency scaling. The idea behind this is that, well, when your CPU doesn't have much to do, it will reduce or modulate the frequency. And doing so implies that you have some model in the CPU for what's important for him or what will cost him a lot. And so it means some power models, but it will translate into timing models as the frequency will change. And thanks to, well, or due to Heartbleed, we can break a lot of crypto, and we can counter some protections for pixel stealing attacks. We have 3 CVEs following the Heartbleed attack, the 3 of them having a CVSS of 6.5. All right, so now let's dive a bit in HQC. So as I said, HQC is a key exchange mechanism, and in fact it's based on code-based encryption. So the code correcting codes which are used in HQC is the same principle as the one used in telecommunications. So first of all, you have a message to send, and you will encode it. So you have the encoding messages represented by M times a matrix G. And the idea is that you have some redundancy. Okay, you have some redundancy, and if you have some error in some bits of your redundant message, so the code word, you will still be able to decode it to the message being sent. So you have some neighborhood around which if you add some error, you can still come back to the message. That's the basic of it. And the idea of HQC is that you use the public key to encode it to some value named V. And it's too far. It's not in the neighborhood of your message. So someone having this V cannot decode it to the message being sent at first. And if you have the secret key, well, in fact, you can recover it by coming back in the neighborhood with higher probability. And then decode it using the code correcting code. So if you view HQC as a scheme, you can have Alice and Bob, and Bob wants to send a message to Alice. And to do so, Alice sends him a public key. Alice has some secret key, which is composed of X and Y. Oh. Okay. And Bob will encode its message, which is MG, and will add some error to compute the V, and it will send also a certain U. And when Alice receives it, she computes V minus UI, which is the part where you comes back in the neighborhood of your code word, and she decodes it. And what we showed is that if you have the V minus UI, which is being leaked, I will see it later, which is being leaked at the beginning of the decoding part, in fact, you can recover the secret key, so X and Y. All of them, all of the low case letters here can be viewed either as vectors, binary vectors, or as polynomials. So what we do on HQC, or what can we do on it? Well, we have done multiple things. First, we showed two side-channel attacks on the SIMD-less implementation of HQC. So HQC was a proposal at the NIST competition, and it won it. And as such, it has two implementations, or at least two major implementations. A reference one, which is not being meant to be used in production, and then an optimized one, which is being meant to be used in production, and which is tempered against some types of side channels, mainly timing side channels. So we showed two side channels on it. First one, a theoretical one at the ISA level, so at the architecture level. And we also have done it on real hardware, but we saw that, well, we have another leakage stemming from the microarchitecture, and so we have another attack. And we also proposed some countermeasures to this. So for the SIMD part, why did we remove the SIMD, or is it still useful? Does the attack still mean something if we remove the SIMD? Well, in fact, if you remove it, you have a portable IoT-friendly version as well. If you don't have a SIMD module, well, you don't have a choice, so it's quite important. And in fact, on the particular function we attacked, if you take it alone, it's even faster without the SIMD part. So it's quite interesting. This work is not the only attack on HQC, and it follows a lot of attacks on it since it's being a candidate in the NIST process. And it's the first one, to our knowledge, only recurring one oracle call. So you have some side channel with perfect accuracy, which gives you what's best. And you only have to run HQC once to get it. And it's a power side channel attack. You had some electromagnetic attack and timing attacks also. What's interesting to see is that you have a lot of reference implementations that are being attacked. So people are attacking versions that are not meant to be secured, neither used in production. So quite easy to attack, I guess. And for the architecture level, well, as we have multiple architectures, in fact, we needed two versions. So we have a variant for this one, specially made for the x86-64 architectures. And both variants works on a lot of architectures with nearly all optimization flags. So it's quite portable for an attack. And for the real case attack, we only need some traces. Like it's not a lot. It's because we have some noise. I will come back to it later. And for the countermeasures, we propose 3 of them. I will also come back on it later. But what's interesting to note is that we can use them to mitigate other attacks. So here's a HQC encoding. So as I said, it's based on concorrecting codes. So you have a message and you encode it. In fact, in HQC, you have to use multiple codes to it. So you do one, and then you take it as the message entry for the next one. And the decoding is the other way around. And what we leak is the V-UY part. So first of all, let's assume that this V-UY is being leaked by my side channel. Okay. So we know this V-UY part. And let's also assume that U is invertible. It's not always the case, but to begin with, we will start with U being invertible. It's easy to show that, in fact, we can recover Y from this, and then we have X, so we have the secret key being used by Alice. Now we showed 2 theorems on U. The first one is a security reduction on U. In fact, with the specific mathematics structure used in HQC, we can view multiplication between 2 vectors as a multiplication between a vector and a matrix, which is the circulant matrix of U. And if you take some U, you can brute force in N, which is being the length of the vectors minus the rank of the said matrix. This value is the number of bits you have to brute force in order to recover Y. So if the rank of the said matrix is low, it's quite not interesting, but if it's high, it's quite interesting. So we showed another theorem, which is that the rank of the said matrix can only take 4 values, 0 and 1 being cases of failure of HQC, so it nearly never happens. Its probability is really, really low. And you have 2 other values, n-1 and n. So in the n case, it's invertible and it's easy to recover. And in the n-1 case, which is happening half of the time, the other half being n, what we showed thanks to the first theorem is that you only have 1 bit to brute force. So I think that most of you can do it. All right, so now that we showed how to recover the secret key thanks to V-UY, let's see how we can get this value. So here is the C implementation of HQC of the optimized one. And it's the beginning of the decoding part of HQC. So what we see here is that we take this value of V-UY, which is in the SRC part, and we take it bit by bit, so it's quite interesting. It's not giving all the side channel, as it's only C code, but we see that it could be interesting, and we could recover bits, each of them 1 by 1, so quite easy. So what we have done is that we have looked at the assembly code being outputted by the compiler, which is seemingly like more or less this in the loop. So you have 2 registers, T0 and T1. And if you look at the values of the register T1 during the execution of the loop, what you have is that you can extract the bits B15 when E equals 14, B15 being a bit of the secret, so it's V-UY. And what's being linked by side channel is the Hamming distance between the 2 values of the register T1 before and after the write shift. And here the Hamming distance is in fact, well, only B15. So this leakage gives us directly 1 bit. And if you look at the previous execution in the loop, what you have is that knowing the the other bits, you can recover the bit being computed. So doing so, you can recover part by part and bit by bit each bits of the v-uy value. So here we have some attack working at least on the architecture level, and we have to see if it's still working at the microarchitectural level, and if it's not being like thrown out due to some weird stuff being done by Benoit, for instance. So when we have reproduced the attack on Cortex M4, what we had is this graph. So what you have in the X, the axis is the variation of the power consumption, and we have made a graph like we have done the computation for bits, and this bit can either take the value 0, which is being the one in blue, and or it can either be 1, which is the part in red. So what we see here is that we don't even need to know what are the other bits value, as we have seen in the architectural attack. We only have to like the only thing leaking, it's even easier because it's the bit being computed. So what you have is the leakage of the v-uy part, but you have some noise, obviously, because the Cortex M4 is not perfect, and the probe is not perfect either. So if you have some noise, and if you have this, well, you can just continue with the attack, and if you do multiple measurements, you will reduce the noise you have on your measurements, and you can recover with more probability the v-uy with a higher number of traces. So you just replay the attack, and with 80 traces, you have like for sure this v-uy part, and so the secret key. The category being marked here are the security levels being defined in the NIST competition. So the category 5 being the most secure, but against the sectional, what can they do? And the first one being the less secure. This graph could be improved either with algebraic attack or with better hardware, better probes and such. All right, so we also have proposed 3 countermeasures. The first one being that, well, the decoding part or at least the beginning of the decoding, which is a decoding of a duplicated Riemann-Muller code, is leaking. So what can we do to as a countermeasure? Well, we can change the decoding part. So if we don't have this exponent sum function that's leaking, well, we don't have the same attack, which is possible. You just have to remove the code, but you still have to protect this other decoding. So here is a minimum distance decoding, and it's easier to protect against side channels using some stuff like masking, but the output is still difficult to get as a masked value. But at least our attack doesn't work anymore. You can also add some noise. So when Alice receives the message from Bob, when she computes the v-uy, she samples some random error, and she adds it to the v-uy part. So when the attacker gets v-uy, he gets v-uy plus the error, which he doesn't know. And so you cannot reproduce the attack with only one oracle call. You have to sample at least two values. So you need at least 2 oracle calls. It's not a perfect attack, but it's still a countermeasure. And you have to make the error. Well, the error should be should have a high Hamming weight. If you add too much errors on it, well, you have more decoding failure rates, so you increase the chances of your KEM not working. So it's quite something to find in order to still have something secure but working. And you can also, in the same idea, do some code 1 masking. So when receiving the U and V values, what you do is that you sample some random message, you encode it, and you add it to the V-UY part. And thanks to the code being used in HQC, the decoding of V-UY plus this message will give you the message plus this sampled second message. So you can remove it after after decoding, and as with the noise part, it also requires an attacker to do at least 2 oracle calls. So it's another countermeasure, and you can do multiple countermeasures. It could be interesting, but they still have some bad points, and they have some overhead to it. For the minimum distance decoding, it's the easier one, and we only have done those measurements about the overhead with the reference implementation, as it was easier, but it's only to get an idea of which one is the easiest, and what's the overhead as a gross part. And the minimum distance decoding is like 5% more, and adding noise is nearly free. You just have your decryption failure rate that changes, so the cost is elsewhere. And codon masking is like between both of them, but codon masking, as it was pinned in the literature, is more difficult to do in a side channel secure way. So that's it. I'm ahead of time. If you have some questions, I'd be happy to answer them.
So Didier tried to trick us with the slide count. Look at the slide counter. We were panicking that we would never finish in time. It's so. Oh yeah, the references. Okay. Good. So.
Well, do you have cryptography?
Questions?
Do you have questions about cryptography? One question.
Thank you for the talk. I'm really sorry, this is a question for the organizers. Could you consider putting the slides in full screen again?
Yeah, we are talking about that.
Thank you. Yeah, nice talk. I'm eager to read the paper. Sorry, the question wasn't for you.
Cédric. Yeah, you love cryptography, Cédric. I know that.
Thank you for the talk. As a countermeasure, it wasn't possible to just modify the problematic function.
Sorry, I don't hear really well here.
Well, you made such an attack because there is a function which is which results in an issue, because if the bit is 0 or 1, there's not the same behavior. As a countermeasure, it wasn't just possible to modify this function.
How so? What do you have as an idea to for the CPU makers, or as a to change the scheme?
No, not change the scheme. As a CPU maker, yes. Most of the time, when there is such an attack on a function, you can modify the function so that the function takes the same time or same CPU consumption, whether the bit is 1 or 0, for example.
Yeah, for the timing part, it's used in cryptography, like the optimized version on HQC standards, or at least the candidates to it, were done as timing, like a time, constant time implementations, or at least for an architecture at the architecture level. For the microarchitecture attack, it's not from the architecture which is leaking something. It's really in the CPU, and you don't have like the microcode. You can change it, and you cannot ask the CPU to do your instructions with the same power, be it from when computing a 0 or 1, but you could effectively change the microarchitecture. Like you could do your own CPU and do it in order to have the same consumption when you do your calculus, but you will have like the area of your chip will grow quite fast, and it will cost you a lot to do so. So it's not really practicable, at least for now. Or if you have a lot of money and area, you could do so, but it's more complicated to do so with the power consumption than it is on the timing case.
One last question, yeah.
I had one question about, so there was a proposition of adding a random message that you would encode and then decode with the original message. Doesn't that just move the problem to when you then have to get the original message? So when you remove the random message from the decoded message?
Is the question that you wouldn't be able to retrieve the good message?
Yeah, because you leak UI plus mg, v minus UI plus mg, but then you have also to remove mg from the message.
Well, the code being used here is linear, so what you will have as when you decode it is the message being sent plus your message that you add when you're receiving the ciphertext. But as you know it, you can just do some basic addition. Here, the addition is quite simple. It's a XOR between two vectors. So if you keep your random message somewhere, you can just sum them at the end of the decoding.
Yeah, but I mean, so the attacker leaks UI plus mg, and then the victim still has to like XOR the two, and then that would leak also this trace, and the attacker could correlate this?
It may leak, you may have more instruction that could leak the message being sent by Bob, but your secret key, the one kept by Alice in order to decode the message Bob sends you, this part is sidechain free. So it depends on what you want to secure, and we took the part as an attacker wants to retrieve the secret key and not the message being sent. But it could be also interesting to view the message as a future key, as HQC is being used, or at least meant to being used as a key exchange mechanism. It was out of the scope of this paper.
Thank you.
Okay, so thanks again, Nathan. It's time for break.
Thank you.
The speakers of the next session, can you come and see us to check your presentation? Thank you. So 30-minute breaks.